Let us first acquaint ourselves with the term polymers before we study their classification in detail. Let's discuss the origin of the term polymer. Mer is derived from the Greek word for unit or part. Poly comes from the Greek word for many. So, a polymer can be defined as a compound in which smaller units, called monomers, combine to form a larger unit. In other words, a polymer is formed when many monomers are linked together in a chain. Thus, a monomer is the building block or repeating structural unit of a polymer. Monomers are simple, reactive molecules. They join by covalent bonds to form polymers in a process called polymerization. Polymers are extremely large molecules with high molecular masses. For this reason, they are also called macromolecules. Polymers have a wide variety of applications. In fact, the use of polymers marked a revolutionary step towards modern civilization. Polymers are used in the manufacture of plastic buckets, plastic cups and saucers, children's toys, and synthetic clothing material. Plastics brought about remarkable changes in society and made life easier and more comfortable. Other materials made from polymers include automobile tires, packaging bags, gears, seals, and electrical insulation. Polymers are the basis for 4 major industries: plastics, elastomers, fibers, and paints and varnishes. Polymers can be classified in a variety of ways. They can be classified on the basis of their source, structure, mode of polymerization, molecular forces. Depending upon the source from which they are obtained, polymers are categorized into 3 types: natural polymers, semi-synthetic polymers, and synthetic polymers. Natural polymers are found in plants and animals. They provide much of our food, clothing, and shelter. Examples are proteins, cellulose, starch, silk, wool, resin, and rubber. Semi-synthetic polymers are derivatives of natural polymers. These are obtained from the chemical treatment of natural polymers. Semi-synthetic polymers are not found in nature. Examples are cellulose acetate or rayon and cellulose nitrate, which is highly inflammable. Note that rayon obtained by the chemical treatment of wood pulp, which contains a natural polymer, cellulose, resembles silk in appearance. Hence, it is also referred to as artificial silk. Synthetic polymers are prepared in the laboratory. Examples are plastics, such as polythene or polyethylene, fibers such as nylon, and synthetic rubbers such as neoprene. The manufacture and use of these polymers boosted socio-economic development. On the basis of their structure, polymers are classified into three types: linear, branched chain, and cross-linked polymers. Let us study each of them in brief. Linear polymers are made from long, straight chains. Examples are high-density polyethylene, or HDPE, and polyvinyl chloride, or PVC. Branched chain polymers contain linear chains that have some branches. One common example of a branched chain polymer is low-density polyethylene, or LDPE. Cross-linked or network polymers have connections between chains. These connections are strong covalent bonds that link various linear polymer chains. In order to form the covalent bonds connecting the chains, the monomers in cross-linked polymers must be bifunctional or trifunctional, meaning that they have more than one reactive center. Examples of cross-linked or network polymers are bakelite and melamine. On the mode of polymerization, polymers are classified into two categories: addition polymers and condensation polymers. Addition polymers formed by the repeated addition of monomers containing double or triple bonds. The reaction involves breaking of pi bonds. Addition polymers are sometimes referred to as chain growth polymers. For example, ethene contains a carbon-carbon double bond. When polymerized, it forms polythene or polyethylene, which has all single bonds. Addition polymers obtained from the polymerization of a single monomer are referred to as homopolymers. Polythene is a homopolymer. In contrast to homopolymers, copolymers are obtained by the addition polymerization of two different monomers. Let us draw some simple models to illustrate the difference between homopolymers and copolymers. The first illustration shows many identical monomer units polymerizing into a straight chain homopolymer. The second illustration shows a copolymer with a repeating AB pattern. Two important examples of copolymers are Buna-S and Buna-N. The general scheme for the addition reaction for Buna-S is shown here. 1,3-butadiene and styrene combine to form a butadiene-styrene copolymer. Condensation polymers, or step growth polymers, are the result of repeated condensation reactions between two different bifunctional monomers. Ethylene glycol, illustrated here, is an example of a bifunctional monomer. It is bifunctional because it has two hydroxyl groups. The condensation reactions involve the elimination of small molecules such as water, alcohol, or hydrogen chloride. Illustrated here is the condensation reaction between ethylene glycol and terephthalic acid to form polyethylene terephthalate, or PET. When two different monomers link together, a water molecule is eliminated. Important examples of condensation polymers are terylene, also known as PET, or Dacron, nylon 6, and nylon 6. Consider the two monomer structures shown here. Which would be more likely to form an addition polymer? Which would be more likely to form a condensation polymer? Monomer A would form a condensation monomer. It is a bifunctional monomer. Monomer A is one of the two components of Kevlar, a polyamide. Monomer B has a carbon-carbon double bond. It forms an addition polymer. Monomer B is a monomer of polyacrylonitrile, which is used to make rugs, blankets, and clothing. Based on the molecular forces present in them, polymers are classified into 4 types: elastomers, fibers, thermoplastic polymers, and thermosetting polymers. Let us study them one by one and see how their molecular forces affect their physical properties. Elastomers are rubber-like solids with elastic properties. An elastomer can be stretched to many times its original length. It snaps back to its original length when the external force is released. The polymer chain in elastomers are held together by very weak intermolecular forces. There may be a few cross-links between chains. Many elastomers are copolymers. Examples of elastomers are Buna S, Buna N, neoprene, and natural rubber. Fibers are thread-forming solids. Since these polymers can be elongated into long, thin threads, they have high tensile strength and high modulus, which means that they are strong. Hydrogen bonding exists between the chains, because of which the chains are packed closely together. Examples of polymers that form fibers are polyamides such as nylon 6,6 and polyesters. Which of these diagrams better represents an elastomer? A fiber? How can you explain your answer? Diagram A represents a fiber. The chains are closely packed, which makes the structure crystalline in nature. Hydrogen bonds hold the chains in close contact. Diagram B represents an elastomer. There are some cross-links between the chains, but the chains do not pack tightly because the intermolecular forces are weak. Thermoplastic polymers can be heated to soften and cooled to harden. Plastics that soften on heating and regain their original properties on cooling are called thermoplastic polymers. The chains in a thermoplastic polymer are linear or slightly branched. The intermolecular forces are intermediate in strength compared to elastomers and fibers. When heated, the chains can move past each other, so the sample becomes less rigid. Also, the chemical nature of these plastics doesn't get altered. Note that these plastics can be recycled after use. Some examples of thermoplastic polymers are polystyrene, polythene, or polyethylene. and Teflon, and polyvinyls such as PVC. Thermosetting polymers, once set, harden permanently and cannot be reused. Plastics that change into hard and rigid materials upon heating are called thermosetting polymers. The chains in thermosetting polymers are cross-linked or heavily branched. When heated, they form extensive cross-linking. As a consequence, these plastics cannot be remolded. Additional heating causes a thermosetting polymer to decompose, as the chains are unable to separate. Instead, bonds break. Note that these plastics cannot be recycled or used again. Examples of thermosetting polymers are bakelite, melamine, and urea formaldehyde resin. Notice the extensive cross-linking shown in the structure of the bakelite resin. You already know that the process of joining many small molecules or monomers together to form very large molecules or polymers is called polymerization. In general, polymers are formed in two ways, depending upon the type of the polymerization mechanism or the mode of synthesis by which they are formed. These are addition polymerization or chain growth polymerization, condensation polymerization or step growth polymerization. Let's learn in detail about addition polymerization. In addition polymerization, the molecules of a monomer, such as an alkene or an alkadiene, add together to form a polymer. The polymer so formed is called an addition polymer. This type of polymerization involves a series of reactions, each of which utilizes a reactive particle, such as a free radical, and produces another similar reactive particle. Thus, free radicals induce a chain reaction. This mode of polymerization leads to an increase in the length or growth of the chain. Hence the name chain growth polymerization. Let us now look at the mechanism of addition polymerization. Addition polymerization usually occurs by a free radical mechanism. Free radicals are neutral, reactive chemical species with an unpaired electron. For example, the tertiary butyl free radical illustrated here. We need to take a detailed look at the free radical mechanism for addition polymerization. It starts with a chain initiation step, which actually occurs in several stages. First, a free radical generating initiator decomposes in the presence of light to form free radicals. For example, a molecule of benzoyl peroxide undergoes homolytic fission on exposure to light to form two free radicals. The free radicals then break down further to form a phenyl radical and carbon dioxide. Now, the phenyl radical reacts with a monomer, in this case, ethene, to form another free radical. The next step in the mechanism of free radical addition polymerization is the chain propagation step. The radical generated at the end of the chain initiation step reacts with another monomer, ethene, to form a new and bigger radical. This radical attacks another molecule of ethene to form a still bigger radical. The series of reactions continues. As a result of this chain reaction, the alkyl chain grows longer and longer. The polymerized product forms in the last step of the reaction, the chain termination step. Eventually, chain termination occurs when the product radical combines with another free radical chain and results in the formation of the polymerized product. The formation of polythene is shown here. Let us now look at how some important addition polymers are prepared and their uses. Some important addition polymers are low-density polythene, high-density polythene, Teflon, and polyacrylonitrile. Let's look at each in turn. Low-density polyethylene or polythene is often given the acronym LDPE. To obtain LDPE, it is necessary to polymerize ethene under high pressure in a temperature range of 350 to 570 Kelvin in the presence of a catalyst. Typically, either oxygen or a peroxide initiator, such as benzoyl peroxide, is used as a catalyst. The equation shown here represents the polymerization reaction to form LDPE. LDPE is a highly branched structure, where the branches in turn may also have side chains. The branches keep the chains from packing closely together, and so the resulting plastic is soft. LDPE is chemically inert. It is tough but flexible and a poor conductor of electricity. LDPE is used to make insulation for electrical wiring, besides squeeze bottles, toys, and flexible pipes. High-density polythene or polyethylene, also known as HDPE, is another polymer made from ethene monomers. To make HDPE, ethene is reacted in a hydrocarbon solvent in the presence of a Ziegler-Natta catalyst at a low temperature of 333 to 343 Kelvin and a high pressure of 6 to 7 atmospheres. A Ziegler-Natta catalyst is a combination of triethyl aluminium and titanium tetrachloride. When triethyl aluminium and titanium tetrachloride are mixed in a hydrocarbon solvent, a heterogeneous precipitate forms, which catalyzes polymerization of alkenes like ethene. The catalyst that results has an empty orbital on titanium, which can form a complex with double bond in ethene. These reaction conditions lead to linear molecules that are closely packed together with a high overall density. HDPE is tough and hard. It is used to make buckets, dustbins, bottles and pipes, among other things. Teflon is another example of an addition polymer. The structure of Teflon is shown here. Can you determine the structure and the name of the monomer used to make Teflon? Since Teflon is an addition polymer, it suggests that the monomer contains a carbon-carbon double bond and 4 fluorine atoms. The monomer used to make Teflon is tetrafluoroethene. The overall equation for the polymerization reaction is shown here. Teflon is the trade name for polytetrafluoroethene. To make Teflon, tetrafluoroethene is heated with a free radical or persulfate catalyst at high pressures. Teflon is chemically inert and resistant to attack by corrosive substances. Teflon is used to make oil seals and gaskets. It is extensively used to make non-stick cookware. Teflon coatings decompose at temperatures above 300 degrees Celsius. So, don't use non-stick pans at high heat. Be careful not to scratch the coating and replace pans when the Teflon coating is damaged. Another important addition polymer is polyacrylonitrile. This polymer is formed by polymerizing acrylonitrile in the presence of a peroxide catalyst. The overall reaction is shown here. Polyacrylonitrile produces the commercially important acrylic fiber. The trade names for acrylic fibers include Orlon and Acrylan. These acrylic fibers are soft and flexible and produce lofty yarns. These properties of acrylic fiber closely resemble those of wool. Hence, acrylic fibers are often used to make sweaters and other pieces of apparel. Acrylic fibers have good resistance to stains, chemical, insects, and fungi. Can you write the chemical equation that represents the formation of polystyrene from styrene? The formula for styrene is given here. Polystyrene is an addition polymer. This can be inferred from the carbon-carbon double bond in styrene. Polystyrene is commonly referred to as styrofoam. In condensation polymerization, the molecules of a monomer combine with the elimination of simple molecules such as water, alcohol, and ammonia to form a polymer. The polymer so formed is called a condensation polymer. You already know that condensation polymers are the result of repeated condensation reactions between two different bifunctional monomers. Hence, this type of polymerization also involves a series of reactions, just as in addition polymerization, but it differs in the aspect that each step is independent of the preceding one. The series of reactions in condensation polymerization is attributed to the presence of more than one functional group in the monomer. In other words, the formation of a polymer is possible as the monomer can undergo reaction at more than one functional group. The product formed in each step of the reaction as a result of condensation between two different bifunctional monomers also has a bifunctional group that can further react with another monomer to form a larger molecule. The series of such reactions continues. The stepwise condensation of monomers, which results in the formation of a polymer, is called step growth polymerization. Illustrated here is the condensation reaction between ethylene glycol and terephthalic acid polyethylene terephthalate, PET, also known as Dacron. Note that in each step, when two different monomers combine, a water molecule is eliminated. Let us now see how some important condensation polymers are prepared and their uses. Polyamides, polyesters, phenol formaldehyde polymers, and melamine formaldehyde polymers are all important condensation polymers. Polyamides are polymers that have amide linkages. Polyamides may be naturally occurring, such as proteins, or synthetic, such as nylons. Nylons are commercially important synthetic fibers. The general reaction to obtain polyamides can be described as the reaction of diamines with dicarboxylic acids or dibasic acid to form amide linkages. Several different forms of nylon have been synthesized. One important nylon polymer is nylon 6,6. To obtain nylon 6,6, adipic acid or 1,6-hexanedioic acid is made to react with hexamethylene diamine or 1,6-diaminohexane at a high temperature of 553 Kelvin and high pressure. This polymer is called nylon 6,6 because there are 6 carbon atoms in each monomer, adipic acid and hexamethylene diamine, that participates in the reaction. Nylon 6,6 is used to make sheets, bristles for brushes, textiles, and tire cord. Nylon 6, another synthetic fiber, resembles the properties of nylon 6,6 closely. To obtain nylon 6, caprolactam is subjected to prolonged heating with water at a high temperature of 533 to 543 Kelvin. Nylon 6 is known by its trade name, Perlon L. It is used to make tire cords, fabrics, and ropes. Polyesters are another important group of condensation polymers. The general reaction to obtain a polyester is a condensation reaction between a dicarboxylic acid and a diol. Dacron is the trade name for polyethylene terephthalate, or PET, a common polyester. To make Dacron, ethylene glycol and terephthalic acid are reacted at 420 to 460 Kelvin in the presence of a zinc acetate, antimony trioxide catalyst. The structure of the repeating unit is shown here. Dacron is grease resistant. Therefore, it is often blended with cotton and/or wool. It is also used as glass reinforcing material in safety helmets. Can you write the equation for the formation of Kelvar via a condensation reaction from the monomers shown here? These two monomers can form a polyamide chain with para or 1,4 linkages. Notice that HCl is formed during the condensation reaction. Kevlar fibers are very strong as many hydrogen bonds are present between the chains, as shown in the illustration here. Kevlar is used to make protective gear, including bulletproof vests. It is also used to make a variety of sports equipment, including boats and tennis rackets. Besides, puncture-resistant bicycle tires. Phenol formaldehyde polymers are another important group of condensation polymers. The first step to produce a phenol formaldehyde polymer is the condensation reaction of phenol with formaldehyde in the presence of an acid or a base catalyst. This results in the formation of ortho and or hydroxymethylphenol as shown in the equation. In the subsequent steps, the hydroxymethylphenol derivatives react further with phenols to form polymers with rings joined by CH2 groups. For example, the linear structure shown here, known as Novolac, is used in paints. When Novolac is heated with formaldehyde, many cross-links between the chains develop. This cross-linked, rigid three-dimensional structure is called bakelite, the first synthetic polymer that was ever developed. Bakelite can be used to make combs, phonograph records, electrical switches, and utensil handles. Bakelite is also used as a porcelain substitute, such as in game pieces. Another important condensation polymer is the melamine formaldehyde polymer. The first step in the formation of this polymer is the reaction between melamine and formaldehyde, which results in the formation of a resin intermediate. The resin intermediate undergoes condensation polymerization to form melamine. Melamine is used to make unbreakable crockery. It can chip and scratch. However, and it is not microwave safe. Melamine is also used to make fireproof jackets. Note that both bakelite and melamine are thermosetting polymers.